Thank
Got it.
you. Perfect. All right. Thank you. As I was saying, today I'm going to be talking about the image access with the butler in this session number 5 from the Ruby Data Academy 2026. This is a reminder of the agenda, and we're focused on beginner level use of the Ruby Science platform. We're going to be focusing mainly on DP1, but we also will have some sessions about what's to come with data preview 2. And we're going to have also drop-in question and answer sessions. We have two sessions or two schedules at different times to hopefully accommodate most people in the globe. The reference site for the Academy is this GitHub repository, in which you will find the slides, the recordings, and also the recordings and slides materials from previous Academy sessions. So this is a reminder of the community forum, the community.lsst.org. This is monitored by the star if you by the Rubin staff. If you have any questions, please go to the support category, open a topic in the support category. You can ask us anything related to Rubin, to the user data, or anything that you want. There's no questions at all levels, and we're here to help. And then also the questions that you ask are gonna also be useful for other people who probably have the same questions. So we always encourage people to use the forum. So this is a reminder about Data Preview 1, which we're gonna be going through tutorials on this, and we've been using the Data Preview 1 as part of the early science program of the Rubin Observatory. All the documentation, everything that we are saying in this academy, it can be found at dp1.lsst.io. You can find information about how to cite DP1, how to cite every data set, even the camera. And also there is a paper, a very detailed paper that was just recently accepted for publication on DP1. So that's a very useful reference as well. Then in general, for information about the Rubin Observatory, please go to rubinobservatory.org, in particular to the For Scientists section. So for today's agenda, we're gonna go through mainly a hands-on tutorial on how to use the Butler middleware in a Jupyter notebook in the Jupyter aspect of the Rubin Science platform in order to retrieve image data and metadata. So, but first I'm gonna explain a little bit with slides some key concepts and terminology about what the Butler is, and then we're gonna go through maybe at least one, but hopefully it's three tutorials related to the Butler that you can find in the RSP, in the notebook aspect of the RSP. So the Butler is the Rubin's data access systems. You can think of it like in which Rubin user, you ask for scientifically defined data sets. The Butler just finds them, reads them, and returns the right Python objects without requiring you as a user to know any file paths or any formats or storage details. So it's kind of an abstraction. It abstracts away the complexities of accessing data. And you can think of it as an actual butler just bringing you stuff, or maybe you go to a library, you just ask for the book and you don't care what it is, but eventually you get the book. So in very general, so you can think of this as the butler, this user-facing data access system. The butler has two main components. One is like a registry, which tells you about what data exists and how to identify them. So internally, the butler uses this is like a database, and it also has like a data store where the knows where the data are physically stored and how to read and write them. But this is again something that the butler just takes care of itself, and you don't have to worry about that. And an important concept is that of a repository of a repo, which is like a butler managed data environment that contains the registry and data store, a particular registry and data store configuration. So you can create multiple repos. In particular for DP1, we're only gonna have one repo, and that's fine to make life easier, but that's like the general concept. So here, again, a little bit more of other key concepts that don't worry if they seem maybe too abstract right now. We're gonna go through the Jupyter notebooks to see how they actually work. So As a reference, there is this documentation, the Butler documentation. You can go to pipelines.lsst.io middleware, or in our DP1 page, we also have a summary of this Butler terminology as well. So again, I already talked about the repository. The repo, again, you can think of as a directory, but as I was saying, it's not just like a Unix directory. It has like a data store and a registry. So he knows where and how to find things. Another important concept is that of a data set, which is like a singular entity. It's like, for example, an image or a table, and how it is stored. For example, a visit image is like a data set for a single visit, for a particular detector, or an object table for a single tract and patch of the sky. Remember that we have a sky map that is a tessellation of the sky divided in tracks, and the tracks are in turn divided in patches. Then each data set has data set types. So this is like a category, like a visit image or an object that has like a corresponding storage class and a set of dimensions. And then we'll see what those dimensions are. So the storage class is how the data is represented in memory. It could be an arrow astropy tables or something called exposure F, which is a type of data that we have in Rubin as well. The dimensions are these keys that identify data sets for a given type. So you can think of it, at least I think of it as like an n-dimensional space. But these dimensions are terms that kind of make sense from the point of view of you're an astronomer, of a user. I mean, like an instrument, a detector, a visit, a tract, a patch, and a band. And then for each data set and data set types, and they have different dimensions, but then you define the minimum number of dimensions that you need in order to uniquely identify that particular data set. For example, you might say that I need like for an instrument, LSST ComCam, for a particular detector, detector 3, for a particular physical band, then that might be enough to get you what you need. So this is the type of examples of these dimensions. So the dimension records is like a corresponding list of values that they can take. So they represent entries in these lists, and it provides an instance of the dimensions of the subset. In the case of the filters, for example, the bands, you can have U, G, R, I, Z, Y, for example. Sorry. Then a data ID is a combination of keys and values that uniquely identify a data set, which is exactly what I was saying. And we'll see in the tutorials that we're going to go through in a few minutes. You can define a dictionary with this with as a data ID that identifies, that tells like every dimension for a particular data set that you need. Then another important concept is that of a collection, which are different versions of the same data set, because you can run things multiple times, but you don't want to overwrite every time you run something or reprocess something. So then you can have different collections, and then the butler knows, if you give the butler, when you instantiate the butler and you also give the name of a collection, then the butler knows that it should be looking for the data sets in those particular collections. So again, as with the repo, you're going to see in the tutorials that we only have one repo for DP1, and that effectively there is only one collection for DP1. You as a user, you're going to see only one collection. If you poke a little bit, and we'll see, you're going to see a bunch of list of collections, but you don't have to worry about that. Again, don't worry about all this. It's a lot of terminology, but you will see that it will get easier as you play with the data and with the notebooks. So to summarize, you can think of things as the key concepts are like the data set type. It says that the kind of thing that you want. The data ID says which one you want, and the collection says where to look. Another extra reference that I wanted to put is a paper written by one of the developers of the Butler system. It might be a little bit technical. It's not that long. I think it's an SPIE proceeding. So take a look. It gives you a little bit more of the details if you're interested in this. And I believe there is an associated video up to the presentation. So at least I found that very useful. But in addition the documentation here. So, okay, let's go through the tutorials. Yeah, this is the end of the presentation. As a reminder, don't forget to fill out the exit survey at the end. But we're gonna go to the RSP, the Ruin Science platform, to the notebook aspect in this case. I'm already signed in, so it's not gonna ask me for my credentials, I hope. Let's see if I can put presentation mode. Then the cool thing about the tutorials is that you can find them right here very easily. Well, let's go to DP1. This is in the 100 series, Butler data access. And then we're gonna try to go through these three, maybe four. Let's see how it goes. So let's do the first one, get it started with the Butler. Okay. So yeah, all of our tutorials follow the same standard, and then we tell you about our learning objectives, the data products we're going to be working on with a deep coat, visit image in this case. And we have an introduction about the butler. Again, it's an interface or something that is abstracting the complexities of accessing data for you. So it's the LSST Science Pipelines interface for managing, reading, and data sets. So you can access both. If the butler enables you to access to search and retrieve data based on its properties like a sky location, band, date, and then you don't need to understand exactly where things are or how they're stored. As a general rule of thumb, it is recommended to use the butler when accessing image data in the notebook aspect of the RSP. Um, if you're actually running the LSS designs pipelines, it might be that you want to do some reprocessing and then you want to, this is all open source code, so you could in principle run your task within the LSS designs pipelines on images. Then you need to know to use the butler in those cases, but that's in that instance. But then for most of other user cases, we use the standards of IVOA, the International Virtual Observatory, International Virtual Observatory, like table access protocol and the simple image access. So just to back up a little bit, that's the other way that you can access data. But here we're focusing on the butler. So here we're demonstrating how we create an instance of the butler in a very basic way in order to search and retrieve for images. So we start importing the relevant packages, in particular the butler from the LSST science pipelines and some other code that will help us deal with time spans. Then code in order to display the images that we're going to see, and then AstroPy time module. So there are multiple ways of doing image display, and I believe that's one of the sessions in this academy. Maybe the next one after this, we're going to use something called Firefly here. You can see it looks very similar to the portal, but once you use AFW display, you set the backend, you can do Firefly. You could also do Matplotlib, but in general, we use Firefly. Maybe we can do something like this. Okay, just put it here. All right, so just to make it a little bit bigger. I hope this is big enough, but if not, let me know and I'll try to make it bigger. Okay, the first thing is that we're gonna create an instance of the butler. So we already imported the butler. As I was mentioning, for DP1, we only have one repository, it's called DP1. One relevant effective collection is called LSST ComCam DP1. And then that's it. You don't need to know exactly how this works, but the collections, this is telling the collection, look for the data in this particular, this is telling the butler, look for the data in this particular collection. So we instantiate it, we do an assert that we didn't get an error, And then the first thing that we're gonna do is to query and retrieve an image. So a most common query, it contains like a sky location and then a band, a pass band and an astronomical band. Then you can choose the type of image that you want. We were talking about in DP1, we've had different types of data products. For single epochs, we have visit images. Then for the stacked images, we have deep co-added images. You give the constraints for your query, like coordinates, band, the time of observations, and then the butler looks for that type of image under those constraints, and then it gives you data that meets those constraints, and then you use that information that you got back from the butler in order to retrieve an image. In our DP1 tutorials, we use frequently the extended Chandra deep field south as one of our examples, as one of the fields, the deepest field. So we declare the coordinates, we declare the band, and then we're gonna define a query in order to pass it to the butler. So there are tutorials that demonstrates to how to figure out all these names and these patch regions, but then um, well, for now we're defining this query here that includes the band and the point that we defined. And we're gonna use you can start poking the butler and the functions that it has, and then, for example, we can start looking at the dataset references. So we can query. We're interested in deep coats, and then that are gonna meet this query constraint. So there's a function called query datasets that is gonna give us like what we call dataset references. That kind of you can think of it like pointers. You can poke at it. Let's see, dataset refs, and then it gives you kind of like a pointer with information. You can start looking at the dataset type that it has, the dimensions that it has, the type of exposure, and then even more details about what is kind of stored. You don't have to care too much about those details. It's just you can just look at it. But then once you pass the query, we did that query for the butler. We got those references. Then we use the first one of those references. We use one of those references to retrieve the image associated to that particular reference. So again, it was like a pointer, but here now we have this deep coat. Again, you can use whatever you want, but we recommend using Firefly, and that's what we're using right now here in this tutorial. And then you can start looking at it, and that's what we got. So yeah, it does look like a pretty nice coat. So that's one way of visualizing a coat, just using the butler, defining the query, defining the dataset type, and then using the reference in order to do the image. So now that was for a coat. Let's say that we're interested in a visit image. So first we have to again define the constraints. In this particular case, we define a time span. Using this particular, we use the time module that we imported. Then we define the time in a particular format, this ISO-T format, and then this is in the International Atomic Time. So we define a time span right here. And then, yes, assuming that you know the time span, so that's like a different question, but here we're assuming that we know that. Here we demonstrate a slightly different way of placing the constraint. There is something called the bind functionality, in which you can define the parameters in a dictionary, and then you can pass them to the butler using colons. It does have this particular syntax. So here we're going to use the same query query datasets function from the butler. In this case, we're going to be looking for visit images. And then the constraint here is going to have all this. It's similar to the constraint that we have up there. Is AD is similar to ADQL, but it's going to have these placeholders separated by colons here, the location, the band, the time span. Then you can pass in this bind dictionary. So it's just going to replace those values in that query. And then you can actually tell it how to sort the results, in this case by observation time. So again, we got a set of references, and we can use for illustrations. We can pick the first reference for that for what we got there in order to. In this case, we're gonna use get. I guess I didn't mention that explicitly, but that's what we use here. Butler.get in order from the reference in order to get the actual image. And then again, we use Firefly. We can reuse the same frame that we already had. And then we got a visit image, which is a single epoch image. It's not co-added. And then you can also tell by either it's not like a co-added image as well. Okay, but that was to get then we do some cleanup here. Okay, but that was to get the coat and then now to get the single epoch images. Then we can also get an image using a data ID, which I was mentioning. You can define it as a dictionary, and then the components of of that dictionary will uniquely identify a data product of a given data set type. And so in this case, okay, let's do it for the deep coat and the minimum amount of information that you need for a deep coat is going to be the band, one of the LSST filters. Then the sky map that you use for DP1, we have a single sky map. So we tell you that in the documentation is this sky map is a tessellation of the sky I was mentioning before that this tessellation is divided in tracks, which in turn are divided in patches. So you define, so here this is something that we're going to define. So but let's go back here a little bit. So these are the four pieces of information that we're going to need to get a deep coat. So again, we define the coordinates, the band. I think we have to redefine them because we deleted them, but that's fine. Um, And then here, we're demonstrating, well, how to get the data set references in order like using the same query data sets that we did before. We can get the information about the tract and the patch number that we need that we can use in this case in order to define the data ID dictionary. So we use this function that we used before. We got the data set references here. Then we loop on the two references that it tells us about the map, the sky map that is going to be the same, and then the particular tracks and patches here is the same track into adjacent patches because they usually they overlap. So that's why there were two of them that satisfied these constraints. So then directly, let's suppose that you know that information directly. This is another way of getting the deep coat passing the information, telling you that you want a deep coat, telling it that you want a deep coat, and then passing the information that uniquely identifies that. So that's one way you can pass explicitly each component as a keyword, or you can define a dictionary explicitly with these values. You need to pay attention a little bit to the syntax, I guess, when you're defining a dictionary, it has to be a string in the key, but other than those details, you can just to be a little bit cleaner, define the dictionary and pass the dictionary, and then again you get the deep coat. So we can look at it again if we want, and then we verify that it's the same stuff that we got before. So that's another way of doing it, passing the data ID um, explicitly as a dictionary or as keywords. Then for visit images, then what you need is the visit identifier and a detector number. We have a visit for each detector. So in this case, we find a visit image, and let's say we want in this particular case, is the image that was taken on November 8th of 2024, the image number 254. It doesn't have to be in this format, but it's informative. It's an integer that is informative. And then you pass it to one detector from 0 to 8. We have 9 detectors in Concam. And then you get the visit image, and that should be enough. Let's see just for fun. If I don't pass the detector, it complains, right? And then you can start getting like a sense. And sometimes it's very informative. No value no value in data ID for required dimension detector. So it's already telling you you're missing one dimension. So that's the kind of thing that if you don't pass enough constraints, that is gonna tell you. Then again, you can do it with the data ID. It's kind of the same stuff that we had before, and then analog in an analogous way to what we had with the decode. We can use a data ID, and then we can look at it again and see that it's that it that it that it is what we wanted. Then the visit image, you got this, we got this object right here, and then the AFW display knows how to use that object and then just give us the image that we want. But again, it's an object, you can start poking it, and then you realize that you can get the filter, for example. Then we're gonna start getting a little bit into the subtleties because we actually have different dimensions for the astronomical bands, U, G, R, I, Z. But in principle, a broadband could have different physical filters that actually go in the carousel in the camera. So in this case, I think it's just one physical filter, but it does just wanted to point out that it does have a different a name, and that's why sometimes you see a dimension called physical band and not just band. Other piece of information, you have a visit info object attached here that it has a lot of cool metadata, and then you keep poking, and then, for example, you can get the date of observation and in the coordinates. So in the convention, the International Atomic Time. So okay, we clean a little bit. So that's for that. Let's say sometimes for efficiency, you can tell the butler not to give you the whole visit image that has the actual array of pixels that shows the image, has a variance plane, has a mask plane, has all this metadata attached. Sometimes you just know that you want the filter, and then you can directly actually just request the filter here via this syntax. So in this case, again, you still need to give the unique identifiers, but you just tell it, give me the filter directly, just to retrieve that particular metadata, and then it does give you that. It looks trivial in this example, but it could be efficient in other situations as well. Okay, then if you feel inspired, you can do the exercise for the learner. So that's our first tutorial. Maybe while I pause, let me know if you have questions or in the chat. Um, okay, I think there is another question from the previous session. That's fine. I'm gonna open the next tutorial, but feel free to raise your hand in the meantime. So the other one, sorry, Butler data access. So we can explore the Butler repository here. Okay. We use one function called query data sets, but we'll see that there's a lot more to it that you can use and explore. So okay, in this second tutorial, we're gonna explore a little bit more the Butler collections, data sets, the dimensions, and even the schema. So again, this is the Butler, is this LSST Science Pipelines middleware for managing, reading, and writing data sets. And the word middleware comes from, because this is like an interface between the pipelines and the data. So that's why you see that word multiple times. So let's see how in this tutorial, how we're going to discover what kind of data is accessible and the schema and which dimensions to use to query and retrieve data sets and how to visualize metadata. So we import relevant modules and code. So here we have the Butler. Then we have some packages that will help us deal with geometry and visualization from the LST Science pipelines. We have a defined set of color symbols and line styles per filter, and then some matplotlib standard functionality. Then again, um, excuse me, many of our tutorials you will see start the same with defining the butlers or the ones that use the tab service or other type of service will use that. But in this case, we're doing the butler again, the same repo, DP1, same collections. DP2 will probably be something very similar. We're gonna tell you which is gonna be probably called DP2 and the similar simple collection like that, just to make things easier for users. Here we're defining our color palette, colorblind friendly color table, and then the filters. And then we're gonna start here exploring the butler. Okay, so we defined the repository with I'm sorry, instantiated like we create an instance of the butler using this repository and this collection. And then that means that any queries for the data run with the butler would only look into in that collection. But then we can learn more about that collection. There is an option, there is a function here, a method called butler.collections dot query underscore info. So it tells us the name of the collection, the type of collection. In this case, is something called chained, and it's again a little bit more technical. There are different types of collections, but in this case, it means that it is chained to other collections, and the order in which they are defined, it matters. Like the butler in this collection, if it's a chain of collections, it's gonna look for the data sets first in the one that is more to the left. I mean, it has an internal order. But then again, this is like another detail, but I think it's telling us here the type of collections to which it's chained. This is again curiosity. You don't need to worry too much about these details, but I think it's interesting, and this is the type of other collections to which is changed. Okay, then you can explore if there are other type of repositories and collections that exist. So that butler, you can ask it, do you know any other repos? So yes, it seems that we have two repositories here. Um, the one affiliated to DP1, the one that we're using, but then the other repository is defined for the data preview 02, the simulations, data preview 2. The repos could be remote on the cloud or somewhere else, so we don't know. That's the point. That's fine. We just know the names in case you wanted also to access the DP2. And then if you go to the tutorials of DP 0.2, then you'll probably find that the repo that is used is like this. You can look at all the collections that a butler has, but it's like in like as a warning. That's why is this collected. It's gonna be a very long list, probably. Maybe in this case it's not that long actually, but it tells you the collections that are available to it. And then again for DP1, we only have to care about this. But if you want to look at other collections out of curiosity, that's what the list is. You have find some calibrations here, but I bet that we can also retrieve calibrations from this DP1 collection. I know, yes. Okay, so let's clean a little bit. Then look at the dataset types. Let's learn a little bit more about the dataset types. So commonly used dataset types, we already talked about the deep coat, the visit image. For the deep coat images and the single epoch visit images, but then for the catalogs or tables associated to this type of images, we can have the object table or the source table. Sometimes I use the word table, sometimes I use the word catalog. You can actually explore every list of this is actually a very long list of every possible data set type that you can find. And then it did give us a warning that it was going to be long, but I just wanted to show you just because it is interesting to know. This is like um, the list of data sets that have been defined ever. Actually, it's if you want to remove one of these, it's kind of an involved process. You don't need to worry too much about that. But but yeah, it can be overwhelming, right? So that's why, well, we're telling you how you can do your search. That's fine. You can do it on your own. But we do have in the documentation, like if you need to an object table, this is the data set type. If you need a deep code, this is the data set type. That's why we have the tutorials and the catalogs. Okay, and also this doesn't mean that all these are like well defined. They might be like empty at this point or something, but for you as a user, we're telling you which one you should be using, in particular for DP1, and will be the same for DP2. But also it's good that you know how to poke the butler. Here, for example, I recognize this, the monster. This is the astrometric and photometric reference catalog that is used in DP1, and it will be used in DP2, and that there's a tutorial on that. Then another cool thing is you can pass wildcards here, so you can use the same function. You can query the registry that I was telling you was associated to the butler and query the dataset types, and then you only want to know about the ones that have coat in their name, so that gives you something more manageable. Um, Another one about that has the keyword map. If you're interested about survey property maps, we do have a tutorial about survey property maps. So we have PSF size, differential chromatic refraction, etc., etc. You can take a look at it. But that's how you start learning about the type of data sets that are available. And in our tutorials, we just tell you a lot of the times you use this data set type with this particular name, and sometimes it makes and may not doesn't make sense. But most of the time they have descriptive names. But this is one way of getting to know more what it's in there. And this is another example with the object name. So it's kind of the same. So for dimensions and elements, so the commonly used dimensions, you can define bands, track. As I was saying, the dimension, as I think of it as an n-dimensional space, and every axis on this n-dimensional space is something like this. But it's the idea, the purpose of when the plotter was created is that these are things that make sense for an astronomical point of view. You think about an instrument, you think about a detector, a visit in this case, the track, the patch, the band. And then this, what we call elements, which is a concept associated to dimension. It has to do more, you can think of it, I guess, as an extra dimension, but it tells you more about like the metadata as well. Then you can learn about what dimensions are available in there. So here we give you the commonly used connections I'm sorry, dimensions that are defined. This is what is called the dimension universe. When you see the band, then you see a lot of these other types of, there's a lot of these ones. These have to do with tessellations of the sky. This is the hill peaks pixelation of the sky, and then this is HTM, which is, I think, hierarchical triangular mesh, which is another way of defining pixels on the sky. But then you have multiple versions of them because you have different resolutions. So, but if you see past this, let's say you have band, hill peaks, HTM, and then instrument, sky map, day of observation detector. So this is giving you a list of the dimensions that are known to the botter in its dimension universe. That's the actual term. So here, this is, you can see the physical filter that I was telling you about that is different from band. So that's another cool thing. The elements, you can see it's kind of the same thing, but it has like some extra kind of elements that have to, I believe, with metadata as well. Okay, so for example, now we can look at the dimensions that the deep coat datasets that has. And then you can do butler get dataset type deep coat, and then it tells you, of course, the name that we just specified, but it tells you the dimensions that it requires. So we already showed this in practice, but like if you know this, but then here you're saying we're figuring out how to actually get these dimensions and know that for each data set types which dimensions are required. Um, you can use this for each dimension key. You can use the dimensions.data coordinate keys attribute. So yeah, you can get all the keys for the dimension, and then we can do something analogous for the visit image. So these are the kits that you could use to define a data ID dictionary and pass to the butler. Then there is a minimum set of dimensions that are required. I think, of course, the more information you give, the more constrained um, your query will be, or your request to the butler. But then there is a minimum set of dimensions that needs to be met. I guess you could pass extra information as well to be more constrained, but there's also a method that tells you. once you get the data set types here for you use butler.get data set type for this particular data set, and then you loop over the dimensions, and then there is a method here that tells you um, about the required data dimensions for that particular data set. So in this case, we need to know at least an instrument, detector, and visit. And now, okay, for the schema. So the set of dimensions for these given dataset types have a schema which define how the butler or the query for a given dataset type can be constructed. So here we can also look at this schema for each dimension of this, in particular for the deep coat dataset type. So then again, we use the get dataset type function. We loop over the dimension, and then we call data coordinate keys, and then it's giving you, then we can print the schema for each one of the dimensions that we're looping. And then we have for the band dimension, then we have that the band should be a string. For the a sky map dimension, then the name is a string. Then we have the hash of the sky maps parameters, then and the maximum track number, and then analogous numbers for the patches. Same. Then we have the track dimension. It tells you the schema for that one, the types of each of the components of the schema, and then for the patch dimension as well. So this output above shows us, for example, that a query for a deep code images can be constrained by the track and the patch ID, which are the unique integers, or with something called like a region. But there's going to be example below on this. So we can do something analogous for the visit image. Let's let's just do it here just for illustration, but then you can see something analogous for that, and as well for the object. So you just need to use the different type name of the data sets here, object and visit image. Then the dimension records. So here we can return all the records for a given dimension in the collection. So that means like all unique instruments, bands, tracks, patches, visits, and detectors. And then in the case for example, for the instrument, then we have this maximum type of records for the LSST. For DP1, we only are gonna have one instrument, so it's gonna be this LSST COMCAM. But you could conceive, or there are other situations in which you have more than one instrument. So here it's telling us about the dimension records for the band. In this case, this is the type of these are like the acceptable names that you can give to that dimension, to that particular dimension. So in this case, we have the 6 bands, and then I guess probably 2 other bands that were used for testing or engineering, then even an unknown band. But of course, we're gonna use mainly these 6 ones, U, G, R, I, Z, and Y. So okay, here, okay, print the unique tracks in the DP1 collection and see that we only have like 31 tracks because the DP1 probably is covering a relative small area. So in this case for DP1, we can do that. We have like 7 fields, 1.5 square degrees total, but we could query the dimension records for the track that are defined in the butler and see which ones of the tracks, like this is an exhaustive list of the tracks that we have. And then again, um, this is a number that is not like a crazy number. For DP1, for DP2 and other data releases, we're gonna have something larger, of course. You can get all the visits for all the detectors IDs as well. So getting that this is gonna be oh no, it's not a lot this, but it just tells you, actually it's just the length of this what we're printing here. I thought we were gonna print the whole thing, and I'm glad we didn't, but okay. So here it's telling us that in DP1 we had almost 1800 visits. So this is how you know, like many of the numbers that you see in the DP1 paper, they could be calculated like this with the butler. So this is one particular number about the number of visits here. You can do something with the detectors. That's not gonna not let's not do that for now. The data IDs. So the data ID, as I was saying, is a dictionary that has as keys all the dimensions and the values that uniquely identify a data product for a particular data set type. Again, for a deep coat, then we have the band, the sky map, the track, and the patch as the keys, and then the records that we have to specify. Um, Here we have the option to print all the unique data ID values for a particular instrument, band, and track. So in this case, this is similar to what we already have in the previous section. In this case, for the instrument, we just have this LSST COMCAM, and then for the bands, these 6 bands, astronomical bands, in addition to these other probably engineering bands. Then we can define the tracks that are defined for a particular sky map. The sky map is the same, is unique for DP1, and then the tracks as well. This is another way of visualizing that. Then we can also look at this information from the sky map point of view. So we get the data set type for the sky map, the tessellation of the sky. We can look at the schema. So again, do get data set type sky map. We get the data set type, and then analogous to what we did before, we can loop for the dimensions and the coordinate keys and look at the schema. And this is the same syntax that we used in the previous section, and it's telling us about the schemas. And then, as I was saying, it returns all the sky map records for DP1, which is just one, the LSST cells B1. You can look at the dimension records and then yeah, the hash number, but then you can also retrieve the sky map from the butler itself. And we use this a lot in tutorials, especially for visualization. One of the tutorials to visualize the DP1 fields, then you need the sky map, and then this is the way to get it. So it's called a sky map, and then it actually passes the sky map, so you get the option. All of these uh, objects, they have like a help. You can associate it to it. It actually gets the strings, the information that you got in the actual code. If you want to know more details about the implementation and about where you're getting that Python object that you're getting. You can also print all the methods that are available to up this, in this case, for the sky map. You can just loop over it, and then you have different methods, and then again you can poke with help. Some of these methods, for example, are pretty handy. This one prints the minimum and maximum array and deck covered in a given track, and the track and patch for the array for an array and deck of that particular location. So, okay, well, you see, there's a lot to poke and a lot to learn, and I think I'm running out of time, but I did want to go a little bit slower on this, at least just to show you the type of thing that you can do on your own. So once you get the butler, and then once you get you start poking into the particular attributes in the particular methods, but the take-home message is that, yeah, the butler, you can think of it as this abstraction thing that just gets you the data. You don't have to worry exactly where it is stored, how it is stored. As long as you give it unique identifiers, these the data IDs, in these particular dimensions, then it's designed to make it intuitive and easier for you to retrieve images, catalogs as well. But as I was saying, the rule of thumb, we recommend in the notebook aspect to get the images via the butler, but the catalogs using the tab service. I think I'm out of time. I couldn't go through the rest of the notebook, but I wanted to stop here and see if there are any questions or any comments. I encourage you to keep exploring here, and then the other tutorials as well about the butler. Yeah, sorry, didn't have all the time to go through it, but I did want to go slowly and show you um, all the stuff that you can do. Do you have any comments or any questions? I don't see anything in the chat. I think this is talking about the tracks and the boundaries. This is, yeah, you can also start using a region. Let's see, like well, very quickly what's happening here. We're defining a region, a circle. You can get the dimension records for the track and the patch. It finds the number of patches. This type of code is actually used a lot to visualize each one of the fields that we had for DP1, in the particular case, the Chandra field that we have right now. And then once we get those records for the tracks and the patches, then we can use Polygon and other plotting routines in order to produce a plot like this. And then I believe that the last part of this notebook is showing us this total number of cumulative number of visits by the modified Julian date. That's also another useful using querying the dimension records and then you using the time for a particular time span. Again, on a region of the sky here using from IDO POS. Okay, yeah. I think I'm gonna stop there. Is there any comments, any questions? If not, we can take a little break until the next session. And I do recommend taking a look at the paper and our documentation about all these concepts, but it gets more intuitive as you use it more and more. Okay, well, thank you so much. Don't forget that if you have any questions, you can follow up on community.lsst.org, and we'll be happy to answer any of your questions and don't forget to keep going to the other sessions of the academy. Thank you.